Okay, so this is your second lecture, just to make sure you're watching the right one. This is your second lecture about projectile motion that you should be watching before class on Thursday. And we are going to start to really dive into how to solve these problems. So first of all, before we get into the types of problems, to do projectile motion problems, we're still using the same three kinematic equations that we did in the last chapter. So I'm going to write them in their x form. We use them in x and y. So there's no new equations to know for this chapter. So we see some different scenarios for projectile motion. Again, conceptually, the key to solving projectile motion problems, and the reason that they can work quite nicely, is that the motion in x and the motion in y are independent of each other. So how something is moving with regards to its range, that was the term I was using before, is completely independent to whatever's happening with its vertical height. That being said, there is one variable that links the two. So we said conceptually projectile motion is when an object is in the air. It's the moment, if we were talking about like a soccer ball, it's the moment after it has left my foot until the moment right before it hits the ground again. And so the one variable that is linked between those horizontal and vertical parts of motion is time. So something's going to have to be in the air for the same amount of time in x and in y. And so that's what allows us to solve these problems. So like the last chapter with the vertical situations, for projectile motion, I classify them into three different types. Now remember, when I'm saying types, this is just an approach I personally take to problem solving. So there are absolutely some situations that would fall outside of these. But almost all of the problems that we do, particularly in our first year of physics, will be categorized as type 1, type 2, or type 3. So I want to run through each of those types, just kind of conceptually what they look like, and then we're going to practice with a type 1 and a type 2 today in this lecture. Okay, so a type 1 problem is one that is projected horizontally. And you're actually going to see that word horizontally, or something is fired horizontally, something runs horizontally, something is kicked horizontally. So you see that word in almost every single problem that is a type 1. So you want to, that's a big clue. So what do I mean by horizontally? I mean that the initial velocity is all in x. So that looks like something, this is its initial velocity, and it goes out and falls, like let's say the ground is somewhere below. So an example of a type 1 problem was actually the monkey gun demonstration that I did for you in class on Monday. When I had that apparatus on the edge of the desk and the one steel ball was shot off of the desk towards the front row of the room, all the initial velocity for that steel ball was in x. In other words, I wasn't pointing it up at all or down at all. All of the initial velocity was in x, and it fired out, but at the same time it was falling down. When you do a type 1 problem, you're going to have givens in x and in y down, because it's not going up at all. So you have givens in x and in y down. Time in x is going to be equal to t and y. So it's going to be moving horizontally for the same amount of time that it's falling. As soon as it hits the ground, it stops doing both. And when it comes to the initial velocity, because the initial velocity is all in x, if we think of it as a vector, we are going to look at the x and y components of these vectors. So I'm going to say, you'll see me say v naught in x and v naught in y. So for the type 1 problem, the entire initial velocity is in x, and the initial velocity in y is 0. It's as though it's just dropped, right? Which is again how that monkey gun demonstration worked. There was no initial velocity in y. So this is a type 1 problem. So when we go to solve these problems, again, which you'll see me do in a few moments, so it'll make more sense then, you're going to see me list givens in x and in y down, and it's understood that the initial velocity in y will be 0. So it's similar to a type 1 problem in vertical motion like we did in the last chapter. Okay, a type 2 problem sorry, awkward pause while I erase. A type 2 problem is where you have an initial velocity at an angle and you have a symmetric trajectory. So remember, trajectory is path. A lot of our sports problems are type 2 or type 3. So it would be like this. If I had, it was kind of like the trajectories I was drawing actually in the last lecture that you watched, the conceptual one. So I have the initial velocity at some angle theta. So imagine if I kick or throw or hit a ball up at an angle, and let's say I do it from the ground. So soccer is a good example of this. So I kick it from the ground, it goes up at some angle, and it's going to come back down and hit the ground. So there's symmetry here. So like in the last chapter, whatever's happening in y up is going to happen in y down with opposite signs. For this one, you need givens in x and at least y up. Now because y up and y down are going to be basically the same, opposite signs, but because of that symmetry, you can use just one. Again, just like that last chapter when you would solve a type 2 problem up and down and you only had to look it up, same deal. It's in x for the total time, which is equal to 2 times the time it takes to go up, right? So remember, in the previous chapter, if we could find the time it takes to go up, we would just double that to find total time in the air. It's going to be traveling horizontally that entire time. So to find the range, we use the total time. The other thing that's important here is to look at this initial velocity vector. So the initial velocity when it is at an angle, sorry, I'm looking for a different color marker. Awkward pause while I walk behind the computer and find a, okay. So the initial velocity when it's at an angle, what we want to know, because we're going to be looking at givens in x and y, we want to know how much of this initial velocity is in x and how much of it is in y. And so to do that, we're going to find the x and y components of the vector. So this would be the, oh my, all that pause to find a marker that doesn't even work. I'll just use blue. This would be the x component, so I call it v naught x. And this would be the y component. I'm going to call that v naught y. So to find those components, we use sines and cosines. We're going to use the method that we were using in the beginning of the chapter. So x is adjacent to this angle, so v naught and x is going to be equal to v naught times the cosine of theta. And y is opposite, so v naught y is equal to v naught times the sine of theta. And this is true for actually all type 2 and type 3. I'm going to repeat it for type 3, but type 2 and type 3 problems. So they're almost always, in fact, honors physics always. They're going to give you the initial velocity and the angle. Could make it complicated where you have to figure that out. But they're going to give you the initial velocity and the angle, and you are going to use just right triangle trig to find the components. How much of that initial velocity is horizontal, and how much of that initial velocity is vertical. So you're taking the vector and resolving it into its components, is what we would say. So that's a type 2 problem. The type 3, as you maybe can guess, is like the type 2. So you have the v naught at the angle, but you have a non-symmetric trajectory. So just like the last chapter, I keep repeating that, I think that's the 15th time I've said it so far. Just like the last chapter, these are not necessarily difficult, but they can be long. So if you have an initial velocity that's at this angle theta, like let's say, so in class on Thursday, we're going to look at a punt, in football punt. So they're going to, I think punt, remember my football knowledge is pretty subpar. They're going to kick, I'm going to just stop trying that. It's going to be up from above the ground is the point. So if this is the kicker's foot, but the ball, let's say, is not caught, and it's going to hit the ground at the other end of the field, we see that we have a little bit of a non-symmetry here, right? Because it's starting at some initial height and it's going to come back all the way down to the ground. So when you have the non-symmetric trajectory, you're going to need givens in x, y up, and y down. In x, it's going to be moving for the total time. right? So if we say this is the punt, it's moving across the field the entire time that it's in the air. And that total time is, of course, equal to t up plus t down, but they're not going to be the same because of the lack of symmetry. And to find your initial velocities, neither one is 0, but v naught and x is just equal to v naught cosine theta, same deal. Nothing about this vector changed. I just took it and shifted it up where it started. And v naught and y would be equal to v naught times the sine of theta. So again, they're still just using the same kinematic equations, still setting up givens the way we're used to. It's a little bit long because you have to have the 3 full sets of givens, and you generally have to solve for more of these types of problems. Okay, so right now we're going to practice with a type 1 and a type 2, and that's it. So in your notes, I start with a type 1 problem. Oh, let me reread it myself. Okay. A movie stunt driver on a motorcycle speeds horizontally. Now I put that in italics, but of course in the problem it wouldn't be, but that's my key word. I see the word horizontally, I think, okay, this is going to be a type 1. So a movie stunt driver on a motorcycle speeds horizontally off of a 50-meter high cliff. How fast must the motorcycle leave the cliff top if it is to land on the level ground below 90 meters from the base of the cliff? Okay. So when we start to do, trajectory problems, projectile motion problems, this is where I think drawing a diagram before you start to do anything else becomes more helpful. In the next chapter, I'll make you do it. It's like actually part of the problem itself. We're not there yet, but if you're a more visual learner, I am. I think a diagram can be helpful. So here we have a 50-meter high cliff. Now I'm not going to take it to the level where I draw a motorcycle. You saw my monkey the other day, so that's a motorcycle, the circle, and that's pretty good for me. All right, so the motorcycle's on a 50-meter high cliff, and we want the motorcycle to land 90 meters away. This is clearly not drawn to scale. And the motorcycle is going to drive horizontally off of the cliff. So we want him to drive off. I'm saying him because in this case, I think this is so stupid that we women are too smart to do it. If one of you tries and can figure out a safe way, more power to you. But that's ridiculous. 90 meters. It's almost football field length there. It's ridiculous. Okay, so the initial velocity is all horizontal, and they want to know what does that initial velocity need to be. Okay, let me say one thing real quick before I dive into the problem. Once in a while, I'll see somebody do this totally wrong, and they'll find like this hypotenuse. So we have 50 meters displacement, 90 meters displacement, and they'll find this hypotenuse and call that the velocity. You have to be really careful with vectors. These are displacement or position vectors, right? You can't make a triangle with 2 sides being position vectors and the third being velocity. That's like 2 completely different physical quantities. So you cannot do that. So just FYI, don't be doing that. So instead, what we're going to do is follow the type 1 approach. So when we have a type 1 problem, we're going to list our givens in X and in Y down. And we list these givens just like sorry, I can't write and speak at the same time apparently. We list these givens just like we did with one-dimensional kinematics problems. So I kind of fall into this order where I do initial and final velocity, acceleration, displacement, time. You've probably noticed that kind of cycle going for me. Okay, now for every projectile problem, type 1, type 2, type 3, we always know the accelerations. It's an understood because of that conceptual stuff that I talked about in the previous lecture. The acceleration in y is negative 9.8 because once the motorcyclist drives off the cliff, he's not changing his motion in any way. Nothing he does can change the motion in any way. So his acceleration is negative 9.8. And in x, whatever initial velocity he has, he's going to maintain. So he's not going to, if he hits the gas or something, it really doesn't do anything to him. So his acceleration is going to be 0. Again, type 1, type 2, type 3, they're all the same. We always know that. Okay, so then let's look at this problem and figure out what else we know. We know that he's going to fall down 50 meters. So I'm going to make it negative because it's down. Y minus 1 is negative 50. And we want him to land with a range of 90 meters. And it's a type 1 problem. That entire initial velocity is in x. We don't know what it is. That's actually what we want to find. but this means that the initial velocity in y is 0. Okay, so the question asks us to find with what speed or velocity does he drive off the cliff. So we want to find v naught in x. So if I look at this situation, I have my givens in x and in y. Remember that time is the one variable that can be linked between these two things. So for as long as the object is falling, it is also traveling horizontally. So if I look at this, I don't know enough in x yet to solve. But in y, I have 3 givens. So in y, I could find time. And if I find that time in y, that allows me to do something with x. So that's what I'm going to do. I'm going to find the time in y. Now, I don't need this velocity. It wasn't mentioned. So when I choose my kinematic equations, I'm going to pick one that does not have the final velocity in it, which is going to be the second equation. Okay? So I'm working in y, and I'm going to use the second equation. Y minus y naught is equal to v naught t plus 1/2 at squared. V naught in y is 0. This is type 1 problem. So v naught t is 0. And we're going to solve this equation for t. So I'm going to multiply both sides by 2. So I have 2 times y minus y naught is at squared. I'm going to divide both sides by a. And then take the square root. So t is equal to the square root of 2 times, sorry, I'll put that down. 2 times y minus y naught divided by a. When I put the values in here, this is the square root of 2 times negative 50 over negative 9.8. The negative signs will cancel out, which is good. When we take the square root, we're going to take the positive root because this is time. So time is always positive. Oh, it's 3 point something. Let's see. Or 0.3 something. That's. No, it's not. This is embarrassing to the extreme. I tried to do math in my head and it was a disaster, as it were. Okay, yeah, there it is. 3.19 seconds. Okay, so my time in y is 3.19 seconds. And this is type 1 problem, so time in x and y are going to be exactly the same. So this means the time in x is 3.19 seconds. Okay? So far I've approached y, solved for time, which helps me with x. And now here I am with x. Now, the interesting thing about x, the acceleration is 0 in x. This is going to be true, we're going to come to a conclusion, it's going to be true for all 3 types of problems. The acceleration is 0. Let's look at these kinematic equations. A is 0. So the first equation, if we put in a 0 for A, right, just says v is equal to v naught, which is true, but that's just not helpful. The second equation, if I put in 0 for A, this whole back part of the term, 1/2 at squared, is 0. It cancels out, but that could be useful. The third equation, if I put a 0 in for A, this whole thing cancels, right, or 0, and it's just, again, telling me v is equal to v naught. So for kinematic, or for projectile motion in x, the kinematic equations give us one useful result that we use for every single situation in which we're dealing with x, and that is x minus x naught is equal to v naught t. And the reason is really just the velocity equation. The reason we're doing that is because the velocity stays constant, because a is 0. So if I'm solving in x for this particular problem, I'm going to say x minus x naught is equal to v naught times t. And I'm going to solve for v naught. This is v naught in x that I'm finding. So I divide both sides by t. So v naught in x is equal to x minus x naught, which was our range of 90 meters, divided by t, which is, I shouldn't write t, I'll write the time, 3.19 seconds. And this gives us about 28.2 meters per second, which is crazy fast. It's like highway speed, okay? So that's lovely. Clearly, this person better be well paid, this stunt driver. They're driving off a cliff, highway speed, 50 meters high. That's so when you dropped your eggs, what was that, maybe 7 or 8 meters off the senior patio? 50 meters is really high. So this is nuts. But there you have it. So recapping, type 1 problem, because I'm not going to do the second one. We're just going to practice that real quick in class on Thursday. Type 1 problem, you have givens in x and in y down. You know your initial velocity in y down is 0. You know your acceleration in y and x all the time, all types of problems. and you know that the time in x and y are going to be the same. And so based on that, there's all kinds of things you could solve for, but that's always going to give you enough information to be able to figure things out. Okay, so let's try a type 2 problem, and then I will be finished. That will be the end of this lecture. All right, so the type 2 problem, remember, is one that has an initial velocity at an angle. So I'm skipping, if you're following along in the guided notes, I am skipping on purpose the second type 1 problem. And so let's go to the part that says like example 2, type 2 problem, I think is what it said. I stapled them backwards. Yeah, example 2 of a type 2. And it says, a projectile is fired with an initial speed of 75.2 meters per second at an angle of 34.5 degrees above the horizontal on a long, flat firing range. Determine the maximum height, total time in the air, total horizontal distance covered, and the velocity of the projectile 1.5 seconds after firing. So they don't specifically, I know I read that really fast, so if you, hopefully you have it in front of you on the guided notes. I'll draw it so you have that information again. But they don't specifically talk about an initial height. They say a projectile is fired at, with a velocity and angle on a long, flat firing range. So it's fired at 75.2, is a weird number, meters per second, at an angle of 34.5 degrees above the horizontal. And it's going to go up and it's going to come right back down. So this is a type 2 problem. So we want to find maximum height, total time in the air, range, and then we'll deal with that last part in a minute. When I'm doing a type 2 problem, for type 2 problems you need givens in x and in y up. But before we do that, the very first thing I do, if they give me the initial velocity and the angle, I resolve that into its components. So I'm going to immediately find the initial velocity in x and the initial velocity in y. So the initial velocity in x is equal to 75.2 meters per second, that's the total velocity, times the cosine of 34.5 degrees, because x is adjacent, and the initial velocity in y is 75.2 meters per second times the sine of 34.5 degrees. So I pop this in my calculator. If you're working along with me, depending on what math you're in, you want to make sure that you are in degree mode, remember. You don't want to be in radians. So, oh, I'm in radian mode, huh? I got some weird answers. All right. So I get about 61.97 meters per second in x, and in y, I get 42.59 meters per second. Okay, so again, I think a great first step, whether you have a type 2 or a type 3 problem, if you've got your initial velocity given to you at an angle, find those x and y components right away. All right, now this one, I'm going to set my givens up into x and y naught, or y up, sorry. So we have v naught, v a, x minus x naught, and for x, I'm going to write t total. It's moving horizontally for the total time, and I write that just to make sure that I remember to think about up is only half the time, because I get a little careless. And y up, again, the only thing I'm changing here is writing t up, just to remind myself that this is just part of the time. So before I think about anything, I know, as I said before, for all of my projectile motion problems, acceleration in x, which is 0, and acceleration in y, which is negative 9.8. So right away we know that. The other thing we know is our initial velocity. It was given, and we just found the x and y components of it. So in x, the initial velocity is 61.97, and in y, the initial velocity is 42.59. Now, in x, because there's no acceleration, the initial and the final velocity are the same, right? It just doesn't change. In y up, the very top of the path, the projectile is going to stop for a brief moment in time, right? It's still moving in x, but it stops moving in y. Okay, so this is what we know. And the problem asks us to find maximum height first. So let's start there. This is the maximum height. So I look at this and I say, do I know enough in y right now to solve the problem? The answer is yes. I want to find height and I don't yet know time. So I'm going to be working in y up. I just like to label so I can keep track of what I'm plugging in where. And I'm going to choose the third kinematic equation. V squared is equal to V naught squared plus 2a times y minus y naught. And I'm going to use this to solve for y minus y naught. Since this is going up, the final velocity we say is 0 at the top of the path. And so I can rearrange this equation. I can say negative V naught squared, I subtracted it from both sides, is equal to 2a times y minus y naught. I can divide both sides by 2a. So y minus y naught is equal to negative V naught squared over 2a. Which is, if we put these values in, we just have to be careful to use our y values. So negative 42.59 meters per second squared over 2 times negative 9.8. Now this is a pretty big, like this velocity, 42.59, that's a pretty big velocity. So I'm expecting a height that's, I mean, nothing crazy, but not small. All right, so I get 92.55, that's pretty high, meters for my maximum height. All right, so again, really, like, I haven't even thought about x yet. So in terms of what I'm doing here, this looks like what we were doing in chapter 2. Then the second thing it asks me to find is total time in the air. So I don't know enough over here to do anything with it yet. But over here I can find t up, and if I double t up, that's going to be my total time in the air. So I'm still working in y up. The easiest equation to find t with is v is equal to v naught plus a times t. Again, it stops at the top, so the final velocity is 0. So this becomes negative v naught is equal to a times t. We divide both sides by a. So t, and this is t up, is equal to negative v naught, so 42.59, divided by a, which is negative 9.8. This is going to give me a positive time, which is great, because that's what time should be. And I get 4.35 seconds. So the projectile is going up for 4.35 seconds. The total time is going to be equal to 4.35 seconds times 2. So what is that, 8.7? 8.7 seconds is my total time in the air. Sorry. Then it asked me to find total horizontal distance covered. That's the range. So I'm wanting to find the range. To do that now, I'm working in x. So in x, remember, there's only one equation which is helpful. That's the second kinematic equation. X minus x naught is equal to v naught t. But the 1/2 at squared is 0. So I leave that off. You can write it if you want, but it's 0. And so I can use this to find the range. I don't have to do any algebra. It's just going to be plug and chug. So I'm going to take that initial velocity in x, which is 61.97. I'm going to multiply by t. Make sure you use your total time. It's traveling in x the entire time. So 8.7 seconds. And when I put this in my calculator, 61.97 times 8.7, I get a range of 539.14 meters. It's pretty far. It's over half a kilometer. So whatever this thing is, it's moving. Okay, so I didn't answer the last part of the question yet on purpose, but let me recap this. So classic type 2 problem. We have an initial velocity at an angle. It's going to land at the same height that it's fired from. We're going to set our givens up into x and y up. We find that initial velocity in x and y just using sines and cosines. That will always be the same. We know in y the acceleration right away, and we know it's going to stop at the top. And then based on what information they give us, typically an initial velocity, we can find the other things. In x, we know that the total time is always going to be twice the time that it takes to go up. And then we can use that to find range or whatever else they might ask us for. Okay, so type 2 problems really look just like this almost all the time. Now, the one interesting question it asks at the very end is, what is the velocity of the projectile 1.5 seconds after firing? So that's when it's on its way up, but it's not all the way up at the top of its path yet. And to do that, to find that velocity, We are going to have to figure out the velocity in y and the velocity in x and put them together. So I'm going to erase what I have up. I'm going to leave the given. All right, so we want to find the velocity 1.5 seconds after firing. That's going to be somewhere, I mean, I'm just making stuff up, but somewhere around here. It's on its way up. It's not at the top yet. So the velocity in y, we can say, is equal to the initial velocity in y plus the acceleration times the time. That's the easiest way to figure out the velocity in y. So 1.5 seconds after firing, the velocity in y is the initial in y, 42.59, plus a, which is negative 9.8, times t, which is 1.5 seconds. That's the time they're asking us about. And so this gives me an initial velocity, or I'm sorry, a velocity in y that should be positive because it's still going up. Should be slower because it's slowing down. Yeah, I get 27.89 meters per second. Now, be careful because, yes, that's the velocity in y, but this thing is still traveling in x, right? On its way up, it's still traveling to the right. The velocity in x at that time is 61.97 meters per second because it never changes. So at 1.5 seconds, this thing has a velocity in y and a velocity in x. If you were to find the total velocity, so these are the x and y components of it. If you were going to find the total velocity, you would put these head to tail and find the resultant of these two, like we were doing with vector addition. So x is to the right because it's positive 61.97. Y is up because it's also positive 27.89. So the total velocity is this resultant, the hypotenuse of that triangle, which lines up with what we're seeing, right, if it's around here. So I'd use Pythagorean theorem to find the total velocity. The total velocity would be equal to the square root of x squared plus y squared. So 61.97 squared plus 27.89 squared. So I get a velocity of 67.95 meters per second. So that is the velocity at 1.5 seconds. But we're almost done. But velocity is a vector. You have to give a direction with it as well. So 67.95 seconds. You got to tell me which way it's pointed. So to do that, I would use sine, cosine, or tangent. I'm going to remember how I love sine. So I'm going to say the sine of theta is equal to opposite 27.89. I'm going to leave units out because they're going to cancel. Divided by hypotenuse, which is 67.95. So when I take the inverse sine of both sides, I get 24.2 degrees. So, and again, that's not the same as the angle at which it was initially fired. You're seeing that angle drop till it becomes 0, right, as it moves up towards horizontal motion. So this makes sense. I want to see a number lower than 34.5 degrees. As it slows down on its way up, that angle is going to decline, we'd say. Okay, so velocity, to find the velocity at some point, what I did was found the velocity in x. I always know, or I'm sorry, in y, found the velocity in y. I always know the velocity in x. I can put those head to tail to find my total velocity. So it was a little practice with vectors. Okay, so I'm going to stop there. Now, I only did 2 practice problems, obviously, but this is getting quite long, and you're ready to be done with me, I'm sure. 30 minutes is too long for a lecture. So, just a quick reminder, give me 30 more seconds of your time. You have a homework set due Friday afternoon. As I told you Monday, it's a little bit longer than the ones you've had in the past. You could start that now, or Thursday morning, or whatever. Type 1 problems, you're going to see those words horizontal or horizontally for most of them. So type 1 problems, you could give them a try. You can even try a type 2 if you would like. In class, when I see you on Thursday, I'm going to jump right into problem solving with these. We're going to practice with another type 2 just to make sure you're good with it. And then we'll go through a type 3 together before we do the lab. So you should be, besides the type 3, there's only one in that homework set. You should be able to attempt to set up all of the other homework problems if you want to work ahead at this point. Otherwise, I'll see you in class on Thursday.